we are presenting depth any camera, a framework for zero-shot metric depth estimation from any camera. Metric depth is a critical input for physical AI. It has been widely applied to tasks like neural reconstruction and novel synthesis, human activity capture for robot imitation, navigation in real-world environments, and robotic manipulation. However, traditional approaches to metric depth prediction suffer from major drawback. 3D perception does not generalize to new cameras when learned 3D priors are tightly coupled with camera's intrinsic and distortion parameters. As a result, each camera typically needs its own dedicated model trained on data collected specifically for that setup. Without a unified model, applying metric depth estimation to new cameras becomes costly and inefficient, requiring both new data collection and model retraining for every new camera. To overcome the limitation, we introduce our method, Depth Any Camera, or DAC. DAC is a unified metric depth model that is trained only on pinhole camera datasets, yet it can generalize in a zero-shot manner to unseen camera types, including fisheye and 360-degree cameras. An intuitive core idea of our approach is to use ERP as a canonical space to represent images from any camera. Because ERP spans 360 by 180 degrees, it can effectively cover the full FOV of almost any camera, including fisheye and 360. With this representation, we convert all images, regardless of the camera types, to the same ERP space for both training and inference of the metric depth model. Importantly, camera intrinsics and distortion parameters are only used during the conversion step. They do not influence the model training or prediction directly. While ERP provides a unified representation, naively converting images to ERP has its limitations, particularly when it comes to FOV extrapolation generalization. Most pinhole training images have a very narrow field of view, and after ERP conversion, they only cover the equiaxial region of the spherical space, where distortion is minimal. If we train a depth model purely on these low distortion ERP patches, it will struggle to generalize to the highly distorted, high latitude regions that appears in fisheye or 360 images. Therefore, how do we train a model that can generalize to these unobserved high distortion regions at test time is the first key challenge to tackle. This leads to our first key design, pitch-aware ERP conversion. Rather than using a naive ERP conversion, we leverage the pitch angle of pinhole images to project them onto ERP patches centered at different latitudes. This allows us to simulate the latitude-dependent distortion that naturally occurs in large FOV camera images. By doing so, we transform the problem from an extrapolation generalization challenge into an interpolation generalization challenge, which deep networks are more capable of. Even with pitch-aware ERP conversion, providing diverse training samples, another key challenge is how can we effectively train on data with diverse field of view. Once original images are converted to ERP space, the content coverage varies greatly across examples, depending on their FOV. This makes patch cropping particularly difficult. There is no single crop size that can both ensure high content coverage and no wasting computation on empty background. Such a dilemma, in turn, prevents the model from learning strong and generalizable 3D. To address this issue, we introduce another simple yet highly effective design, FOV alignment. Given a target patch size in ERP space, we adjust the ERP conversion of each image so that the ERP patches are resized to match the FOV of the target, and the ground truth depth values are scaled accordingly to preserve metric prior. In this slide, we show the full DAC pipeline, covering both training and inference. During training, we start with original perspective images from pinhole datasets. These are transformed into ERP space using our proposed components, pitch-aware ERP conversion, FOV alignment, and a simple multi-resolution augmentation. We then train a standard depth model using these ERP patches, allowing conventional supervision with C-log loss. During inference, any input image, regardless of its camera type, is first converted to the same ERP canonical space. The trained model then predicts metric depths in ERP space, and finally, the ERP depth prediction can be optionally converted back to the original camera view. Here we present a qualitative comparison of our method against the prior state-of-the-art method, metric 3D V2, evaluated in the zero-shot setting on fisheye images. The top row shows the fisheye RGB input and the absolute relative error maps for each method. The bottom row shows the corresponding ground truth depths and predicted depth maps. As shown, DAC produces much lower error across the entire image, while metric 3D V2 struggles significantly. DAC can also be directly applied to 360 images for monocular 3D reconstruction. As shown here, given a single 360 image, our model produces a full depth prediction in ERP space, which further leads to a complete point cloud of the scene. The reconstructed point clouds can then be re-rendered from novel viewpoints using virtual camera setups. Quantitatively, we compare DAC against a range of state-of-the-art methods, evaluated across standard benchmarks. In the most differentiating sigma-1 accuracy, which reflects the fraction of well-estimated depths, DAC consistently outperforms all prior methods by at least 50% on every indoor dataset. What's more, we achieved a strong generalization with significantly less training data and a much lighter network. To summarize, we introduced depth standing camera. It is a unified metric depth model, and it enables zero-shot generalization from pinhole trained model to any camera input. Our effective training paradigm built on pitch-aware ERP conversion and FOV alignment enables effective learning under diverse and challenging FOV variations. Please feel free to check our website, code, and paper using the links and QR code below. Thank you for your attention.